It's time to fire up Germany's revolutionary fusion machine. It's a tense moment.
Germany has unveiled its latest innovative nuclear reactor, poised to surpass even the International Thermonuclear Experimental Reactor in the pursuit of clean, unlimited energy. Germany's new nuclear fusion reactor shocks the entire industry. This reactor represents not just a significant advancement, but a revolutionary leap forward in technology that could reshape our energy future. But how does this revolutionary reactor work? And what sets it apart from previous attempts at nuclear fusion? Join us as we explore how Germany is spearheading the nuclear fusion transformation, potentially changing our energy landscape forever. Germany Ultra-Advanced Nuclear Fusion Reactor. Nuclear fusion, the process of merging lighter atomic nuclei to form heavier ones, is a powerhouse of energy production, mimicking the very mechanism behind the Sun and other stars. Scientists have long been captivated by the potential of harnessing this power for peaceful purposes, tracing back to the early 20th century when they unraveled the fundamental principles of nuclear reactions. However, achieving controlled fusion reactions on Earth has presented a formidable challenge, demanding extreme conditions of temperature, pressure, and magnetic fields to sustain a plasma, a state of matter crucial for fusion to occur. The journey of fusion research is a tale woven with both breakthroughs and setbacks, interwoven with international collaboration and competition, tinged with drama and intrigue. The initial forays into fusion experimentation date back to the 1930s, as physicists bombarded light elements with accelerated particles, witnessing the birth of new isotopes and neutrons. By the 1940s, fusion took on a more ominous role, fueling the creation of thermonuclear weapons and unleashing catastrophic power through fusion-fueled explosions. The post-war era brought a shift in focus as the secrets of the hydrogen bomb were declassified, opening doors to the exploration of fusion for peaceful energy production. Various confinement and heating methods were devised, including the pinch, the mirror, the stellarator, and the tokamak. Among these, the tokamak, a donut-shaped magnetic configuration pioneered in the Soviet Union, emerged as the most promising design. Through the decades, nations such as the United States, the United Kingdom, France, Japan, and China refined the tokamak concept, inching closer to the elusive break-even point where fusion power equals input power. The 1980s witnessed the construction of larger and more powerful tokamaks, such as the Joint European Torus, JET in the UK, and the Tokamak Fusion Test Reactor, TFTR, in the US, achieving unprecedented levels of fusion power and plasma performance. Yet these endeavors were not without challenges. Technical, financial, political, and environmental hurdles loomed large. Amidst these challenges, the late 1980s saw the emergence of an ambitious idea, an international collaboration to pool resources, share risks, and collectively pursue the scientific and technological promise of fusion energy. Thus, the International Thermonuclear Experimental Reactor, ITER, was conceived, uniting unlikely partners including the European Union, the United States, the Soviet Union, now Russia, Japan, and China, with India and South Korea later joining the consortium. The ITER project aims to demonstrate the feasibility of fusion as a sustainable energy source, propelling fusion energy to the brink of industrial application. The ITER reactor is designed to generate 500 megawatts of fusion power for at least 400 seconds, achieving a tenfold gain in plasma heating power. This milestone would mark the first instance of a fusion device achieving a burning plasma where self-heating from fusion reactions surpasses all other forms of heating. Moving further away from the early struggles to harness fusion energy, ITER is enhanced by creative design elements. The Tokomak Principle. At the heart of the ITER project lies the Tokomak Principle, enhanced by innovative design elements. With a major radius of 6.2 meters and a plasma volume of 840 cubic meters, the ITER Tokamak stands as the largest and most complex fusion machine ever constructed. Employing superconducting magnets, the ITER Tokamak generates a powerful magnetic field, peaking at 5.3 Tesla externally and up to 6 Tesla internally, crucial for confining and shaping the plasma. To heat and control the plasma, the ITER Tokamak utilizes a diverse array of heating and current drive systems, including neutral beam injection, radio frequency waves, and electron cyclotron waves. The fusion fuel employed consists of a mixture of deuterium and tritium, two isotopes of hydrogen, with deuterium sourced abundantly from nature, while tritium is produced within the ITER reactor itself, facilitated by lithium blankets surrounding the plasma to absorb the neutrons generated by fusion reactions. As ITER propels humanity towards a future powered by clean fusion energy, there is a scientific exploration and international cooperation. ITER Nuclear Reactor Project. The ITER project is taking shape in Saint-Paul-les-Durance, France, adjacent to the Carache facility, one of Europe's largest nuclear research centers. Initiated in 2010 after years of negotiations and groundwork, this colossal endeavor involves thousands of scientists, engineers, and laborers from 35 different countries, alongside hundreds of companies and institutions. With an estimated cost of around $20 billion, the ITER project is set to reach completion by 2025, marking the milestone of achieving the first plasma. It's a global collaborative effort, representing a $22 billion science experiment uniting numerous nations. Upon achieving the first plasma, the ITER project will embark on a 20-year operational phase. During this period, a series of experiments and tests will be conducted to refine plasma performance and demonstrate the integrated operation of the fusion reactor. Additionally, the project will serve as a stepping stone towards the next phase of fusion energy development, the demo reactor. This next-generation reactor aims to harness fusion to produce electricity on a commercial scale. While the ITER project holds great promise, it faces competition from a German nuclear fusion reactor that has made recent advancements. But to grasp the significance of these developments, it's essential to understand the underlying principle of nuclear fusion. Nuclear fusion occurs when two hydrogen isotopes, such as deuterium and tritium, are brought into proximity. Overcoming their natural repulsion, they fuse to form a heavier nucleus of helium. This fusion reaction releases a substantial amount of energy, primarily in the form of high-energy neutrons and gamma rays. The energy released is determined by the mass difference between the initial and final nuclei, as described by Einstein's famous equation E=mc2. The mass difference for the deuterium-tritium fusion reaction is approximately 0.7% of the initial mass. This means that even a small amount of mass can yield a tremendous amount of energy. However, achieving nuclear fusion is an extraordinarily challenging task. To initiate fusion, the hydrogen nuclei must be heated to extremely high temperatures, around 100 million degrees Celsius, to enable them to move fast enough to collide and fuse. Additionally, they need to be confined and compressed to a high density to sustain the reaction. These demanding conditions, known as the Lawson criterion, necessitate significant energy and technological capabilities. One of the most promising methods to achieve the Lawson criterion is through magnetic confinement. This approach utilizes powerful magnets to create a toroidal magnetic field that traps and shapes the plasma, a state of matter where atoms are ionized into electrons and nuclei. The plasma is then heated through various means, such as particle beams, microwaves, or electric currents. The magnetic field prevents the plasma from contacting the reactor walls, thus cooling it down and halting the fusion process. Several experimental reactors worldwide, such as JET in the UK, TFTR in the US, and KS-STAR in South Korea, have successfully demonstrated magnetic confinement. These reactors have achieved temperatures and densities close to the Lawson criterion and have produced significant amounts of fusion energy, with JET reaching up to 16 megawatts. However, they have yet to achieve the break-even point, where the energy output from fusion equals or exceeds the energy input. Nuclear fusion reactors work by creating and maintaining the extreme conditions necessary for fusion reactions to occur. They utilize magnetic confinement to trap and manipulate the plasma, which is then heated to high temperatures and densities to initiate fusion. Additionally, lithium blankets are employed to absorb fusion neutrons and breed more tritium fuel. Despite the formidable challenges, nuclear fusion reactors hold immense potential to provide clean, abundant, and safe energy for humanity. If successful, they could revolutionize the world's energy landscape, offering a sustainable alternative to conventional power sources. However, achieving practical fusion on Earth remains a formidable task, but one of the most advanced reactors is about to be discovered. The magnetic confinement fusion. Magnetic confinement is a method that uses powerful magnetic fields to control and shape the fusion plasma, preventing it from touching the walls of the reactor. These magnetic fields also help heat and compress the plasma, increasing the likelihood of fusion reactions. One of the most advanced designs for magnetic confinement is called a tokamak, which is shaped like a donut. It generates a toroidal, ring-shaped magnetic field by passing a large electric current through the plasma. Another set of coils around the plasma creates a poloidal, twisted magnetic field, resulting in a helical field that keeps the plasma stable. The tokamak serves as the foundation for the ITER project, a major international fusion research initiative. Another promising design for magnetic confinement is the stellarator. Similar to a tokamak in function, a stellarator has a more complex shape and doesn't rely on a plasma current to generate the magnetic field. Instead, it uses a carefully designed set of twisted coils to create the optimal magnetic field configuration. One advantage of the stellarator is its ability to operate in a steady state without the risk of plasma disruptions that can occur in a tokamak due to current instabilities. The Wendelstein 7X W7X project in Germany focuses on the stellarator design. It aims to demonstrate the feasibility of a stellarator as a fusion power plant by achieving high plasma densities, temperatures, and confinement times. Unlike tokamaks, which rely on a plasma current to create part of the magnetic field, stellarators generate the entire magnetic field externally. This means they don't need to induce or sustain a plasma current, reducing the risk of instabilities and disruptions. Stellarators can also operate in a steady state without the need for periodic adjustments to the plasma current. The stellarator concept was first proposed by scientist Lyman Spitzer in 1951, but faced technical challenges such as complex magnetic coil shapes and difficulties maintaining plasma stability. Stellarator research saw a decline in the US in the 1960s and 1970s, but continued in Germany and Japan, leading to new designs and innovations. Recent decades have seen a resurgence of interest in stellarators due to advances in computational power, engineering techniques, and plasma physics. One breakthrough was the discovery of quasi-symmetry, which helps reduce transport losses and improve plasma confinement by keeping the magnetic field strength constant along field lines. This property is achieved through sophisticated optimization algorithms and supercomputers. Several new stellarator devices, including the Wendelstein 7X, have been built or are under construction to test quasi-symmetry and other aspects of stellarator physics. The Wendelstein 7X is the largest and most complex stellarator ever built, with 50 non-planar magnetic coils, creating an optimized quasi-symmetric magnetic field. It aims to demonstrate the advantages of stellarators as fusion reactors by achieving high plasma densities, temperatures, and confinement times. The Wendelstein 7X has already set several world records, including the highest fusion triple product for a stellarator and the longest plasma discharge duration. Another notable stellarator is the helically symmetric experiment HSX, which is the first stellarator to have continuous helical symmetry. This design minimizes neoclassical transport losses and allows for more control over the magnetic configuration. The Large Helical Device, LHD in Japan, is the largest stellarator globally, with a heliotrope configuration that enables high plasma parameters and long pulse operation. It aims to study the physics of high beta plasmas relevant to fusion reactors. The stellarator presents an elegant solution to the challenges of creating and controlling a fusion plasma. It offers advantages over tokamaks, such as steady-state operation and flexibility in magnetic configuration, but also poses challenges like coil complexity and plasma behavior understanding. Using magnetic fields to squash pellets with lasers is a clever innovation, but fusion research offers revolutionary possibilities. Inertial confinement fusion. Inertial confinement fusion is a technique that uses powerful lasers or particle beams to heat and squash a tiny pellet containing fusion fuel, usually made of deuterium and tritium. This process aims to trigger a fusion reaction by igniting the pellet. The pellet is squeezed by the radiation pressure, creating a shock wave that moves inward, increasing the temperature and density of the fuel. Eventually, the fusion reaction occurs at the pellet's center, releasing a burst of energy and neutrons. Achieving a symmetric and uniform implosion of the pellet is the primary challenge in inertial confinement fusion. This requires precise and synchronized delivery of the beams. Additionally, the implosion must be fast enough to overcome heat loss and pressure due to thermal conduction and hydrodynamic instabilities. One advanced design for inertial confinement fusion is the Hohlraum. A Hohlraum is a hollow cylinder containing the fuel pellet irradiated by laser beams entering through holes at its ends. These laser beams heat the inner wall of the Hohlraum, causing it to emit X-rays that uniformly implode the pellet. The Hohlraum concept serves as the foundation for the National Ignition Facility NIF project, which hosts the world's largest and most energetic laser. The NIF aims to achieve a self-sustaining fusion reaction known as ignition by delivering over 1.8 megajoules of ultraviolet laser energy to a Hohlraum in a few nanoseconds. Since its ignition experiments began in 2010, the NIF has achieved record levels of neutron yield, fuel density, and energy gain. Another innovative approach to inertial confinement fusion is the Z-pinch. A Z-pinch device utilizes a strong electric current to generate a magnetic field that compresses a plasma column along its axis. This plasma column can be formed using various methods such as a thin wire array, a gas puff, or a liquid jet, and can be driven by a pulsed power generator or a capacitor bank. The Z-pinch can produce high temperatures and densities and can also serve as a source of X-rays, neutrons, or ions. The Z-pinch is the focal point of the Z-machine project, which is the world's most powerful pulsed power generator experiment in the United States. The Z-machine can deliver up to 26 megajoules of electrical energy to a Z-pinch load, creating plasma conditions relevant for fusion and other applications. The Z-machine has demonstrated its ability to produce high-quality X-rays to drive Hohlraums and fuel pellets, as well as to generate fusion neutrons. Another pioneering effort in commercial nuclear fusion reactor is underway in Germany, waiting to be unveiled. The ultimate Gaus Fusion. In Germany, a groundbreaking initiative called the Gaus Fusion is shaking up the global fusion energy landscape. It aims to construct the world's inaugural commercial nuclear fusion reactor within the next 1 to 2 years. Founded in 2022 by a consortium of European companies, Hailing from Germany, France, Italy, and Spain, Gaus Fusion represents a paradigm shift in fusion technology. In February 2023, Gaus Fusion achieved a significant milestone by securing initial capital through a successful founders' round of financing. This financing not only bolstered their financial standing, but also signaled a pivotal step forward in realizing their vision of a clean and reliable energy source to complement existing renewable energies. At the core of Gaus Fusion's mission is the ambition to spearhead the commercialization of fusion power plants. Their goal, to emerge as leaders in magnetic confinement fusion technology and pave the way for the first industrial-scale gigawatt-class power plant, dubbed the Gaus Giga. The target date for this monumental achievement is set for 2045. To achieve this audacious objective, Gaus Fusion has devised a strategic approach centered on high-field magnetic confinement fusion. This method, renowned for its speed and efficiency in energy production, harnesses powerful magnetic fields to elevate plasma pressure and density, thereby intensifying the fusion reaction rate and subsequent power output. A more compact and cost-effective tokamak design compared to conventional low-field magnetic confinement fusion, epitomized by projects like ITER. Gaus Fusion's commitment to excellence extends beyond its organizational borders. The company maintains a close collaboration with esteemed researchers at the Max Planck Institute for Plasma Physics. Gaus Fusion represents a beacon of innovation in the pursuit of sustainable energy solutions. At the forefront of fusion research, a remarkable aspect of work is in progress for the development of fusion energy, the fascinating physics lab. The Max Planck Institute for Plasma Physics, IPP, stands as a leading hub for fusion research not only in Europe, but also across the globe. IPP boasts two significant fusion facilities, the AEX Upgrade Tokamak in Garching and the Wendelstein 7X Stellarator in Greifswald. For decades, IPP has been at the forefront of pioneering research in various aspects of plasma physics, including magnetic confinement, plasma heating, diagnostics, and control, among others. One remarkable aspect of IPP's work is its role as the program management unit of Eurofusion, the European consortium for the development of fusion energy. This consortium brings together 30 fusion centers from 25 European Union countries, as well as Switzerland, Ukraine, and the United Kingdom, to coordinate fusion research activities on a continental scale. Moreover, IPP collaborates extensively with partners in the fusion research field, leveraging its scientific expertise and technological know-how. This collaboration extends to Gaus Fusion, which benefits from IPP's vast network and infrastructure. Gaus Fusion, in particular, aims to capitalize on existing facilities like the AEX Upgrade Tokamak for its GigaCraft project, demonstrating the practical application of fusion technology. While IPP's focus lies in advancing the scientific understanding of fusion, another initiative, the International Thermonuclear Experimental Reactor, ITER, takes on the challenge of proving the feasibility of controlled nuclear fusion. However, it's crucial to note that ITER, despite its groundbreaking nature, is not intended to generate electricity commercially. Instead, it serves as a scientific experiment and technological demonstration to pave the way for future fusion power plants. One of the key challenges facing fusion research, including projects like ITER, is the availability of tritium, a rare and radioactive isotope of hydrogen crucial for fueling fusion reactors. While ITER will rely on external sources of tritium, Gaus Fusion aims to achieve self-sufficiency through advanced tritium breeding modules. These modules utilize neutrons from fusion reactions to produce more tritium from lithium, ensuring a sustainable fuel supply for fusion power plants. In contrast to ITER's experimental focus, Gaus Fusion sets its sights on building and operating commercial fusion reactors capable of producing electricity and generating revenue. These reactors will be designed to be seamlessly integrated into the existing power grid, operating continuously and reliably to meet energy demands. Gaus Fusion's approach also prioritizes efficiency and sustainability, utilizing high-field magnetic confinement fusion and optimized plasma parameters to achieve higher power output and efficiency. Leveraging on tokamak designs and existing infrastructure is important, but more significant is having top-notch talent and leaders from diverse fields, ensuring a robust foundation for its endeavors. Fusion Supervisory Board. Gaus Fusion is making waves in the scientific community with its groundbreaking initiative, earning widespread support from scientists and institutions deeply involved in fusion research. The company has attracted top-notch talent and leaders from diverse fields such as physics, engineering, business, and finance, ensuring a robust foundation for its endeavors. The Supervisory Board of Gaus Fusion boasts esteemed personalities like Frank Lahn, the President and CEO of Brooker Corporation, a renowned manufacturer of scientific instruments and superconducting magnets. Additionally, Stefano Buono, the founder and former CEO of Advanced Accelerator Applications, a leading radiopharmaceutical company, and Siegfried Russwurm, the former Chief Technology Officer of Siemens, a global industrial conglomerate, lend their expertise to guide the company's strategic decisions. Moreover, the company's scientific advisory board comprises eminent experts like Sybil Gunter, the scientific director of the IP Tony Dunn, the program manager of Eurofusion, and Stephen Cowie, the director of the Princeton Plasma Physics Laboratory, ensuring that Gaus Fusion stays at the forefront of fusion research. Gaus Fusion's initiative is seen as a promising pathway toward achieving commercial nuclear fusion, possibly within the next 10 to 20 years. By adopting best practices from various industries and implementing a public-private partnership model with national and European institutions, Gaus Fusion is moving forward swiftly, aiming to make significant advancements in fusion technology. The company is leveraging rapid advances and innovations in fusion technology, including superconducting magnets, plasma heating, and control systems, as well as artificial intelligence and machine learning to propel its mission forward. Furthermore, Gaus Fusion is capitalizing on the favorable political and social climate for fusion energy, driven by the escalating demand for clean and sustainable energy sources, heightened awareness of the climate crisis, and a resolute commitment to achieving net-zero emission goals. Gaus Fusion stands as a bold and exhilarating venture that is reshaping the landscape of fusion energy and challenging conventional norms. Collaborating closely with researchers at the Max Planck Institute for Plasma Physics, the company is poised to commence construction on the world's first commercial nuclear fusion reactor within the next 1 to 2 years, marking a significant milestone in the quest for clean and limitless energy. While an important achievement must have been recorded in achieving clean energy, a mission to create the first fully improved device is about to be discovered: the optimization of enhanced stellar radars. The initial try at making a better stellar radar happened at the IPP branch in Garching, near Munich. Called Wendelstein 7S, this early version was working from 1988 to 2002. Surprisingly, by 1993, it had already beaten all previous records for machines of its size, setting a new standard in performance. Encouraged by Wendelstein 7S's success, researchers at UW-Madison started a mission to create the first fully optimized device. Their efforts led to the development of the helically symmetric experiment HSX, a small machine that began operating in 1999. David Gates, an expert on stellar radar physics at PPPL, recognizes the groundbreaking achievements of Wendelstein 7S and HSX, confirming their validation of the optimization concept. Motivated by these successes, researchers in the United States felt empowered to pursue bigger projects. In 2004, PPPL began building the National Compact Accelerator Experiment NCSX Using a different optimization method from IPP, NCES-X faced challenges in putting together intricately shaped parts with millimeter precision. These difficulties increased costs and caused delays, leading the Department of Energy to cancel the project in 2008 despite significant progress. Looking back on the setbacks, George Hutch Nielsen, the manager of NCES-X at PPPL, admitted to underestimating both the financial implications and the timeline. The effort encountered unexpected obstacles, highlighting the complex nature of stellar radar development and the importance of careful planning and execution in such projects. Well, regardless of the setbacks, an ideal magnetic field shape to confine plasma is on the way. The magnetic stellarator radars. Stellar radars, unlike other fusion reactors, have a built-in safety feature. Their magnetic fields are generated externally, eliminating the need for internal pulsing and the risk of disrupting plasma currents. Despite challenges, some teams continue to explore this concept, drawn by its inherent safety measures. Notably, the Large Helical Device LHD in Toki, Japan, operational since 1998, stands as the largest operational stellarator globally. This design, a modern twist on the classic accelerator, employs two helical coils to manipulate plasma and additional coils for enhanced control. The LHD boasts numerous performance records within the stellarator realm, excelling in steady-state operation and nearing parity with tokamaks of similar scale. Pioneering researchers, including Jürgen Nuremberg from IPP and Alan Boozer, formerly of PPPL, now affiliated with Columbia University, proposed an innovative approach to stellarator design. By crafting a magnetic field with constant strength but varying direction per helander, they envisioned a quasi-symmetric field capable of containing plasma with minimal losses. While not a perfect particle trap, it offers promising results, potentially rivaling tokamak's efficiency. This design philosophy, termed optimization, revolves around crafting an ideal magnetic field shape to confine plasma effectively. Achieving this requires substantial computational resources and intellect, a feat that wasn't possible until the advent of supercomputers in the 1980s. The pursuit of fusion energy through stellarators exemplifies a fusion of scientific ingenuity and technological advancement. These reactors, harnessing the power of magnetic fields to control and contain superheated plasma, hold the promise of limitless, clean energy. With each breakthrough in design and engineering, the dream of fusion energy moves closer to reality, propelled by the dedication and brilliance of researchers worldwide. Interestingly, recent progress in nuclear fusion technology is getting attention in the industry. The promise of fusion energy. In the coming years, it's important to guide the world towards emitting fewer harmful gases, especially since the need for energy is expected to triple by the end of the century due to more people, urbanization, and better access to electricity in developing nations. Russia's recent actions have shown the need for more energy sources beyond limited options. While fossil fuels have powered much of our past, they also create greenhouse gases and pollution. Nuclear fusion has become a promising solution for sustainable, clean energy, but making it work globally is hard. Germany's recent progress in nuclear fusion technology is getting attention in the industry. Fusion, unlike splitting atoms used in current nuclear plants, has the potential to provide endless clean energy without long-lasting radioactive waste. Most fusion reactor ideas aim to mix specific hydrogen types to release huge amounts of energy. The Max Planck Institute for Plasma Physics in Germany has been leading the way, making the Wendelstein 7X stellarator. This complicated reactor aims to copy the Sun's energy production on Earth, giving hope for limitless, clean energy. The Wendelstein 7X reactor is an impressive feat of engineering, made with supercomputers and using advanced magnetic coils to hold the plasma. Recent tests have shown good results, reaching temperatures much hotter than the Sun's core, with less heat loss. Although challenges remain, This progress shows a possible future where clean, safe energy is widely accessible. While the road to practical fusion energy may be long and hard, ongoing efforts are small steps toward a sustainable, carbon-free energy future. Which of Germany's new nuclear fusion reactors do you find interesting? Let us know your answer in the comments section. And if you enjoyed watching this video, make sure to give it a thumbs up and subscribe to the channel.